All right, so today the main theme is something called reduction of order, which is exactly what it sounds like. I'm going to take something second order and make it into a first order problem using the appropriate substitution. And then hopefully that problem is easy to solve. Now, I'm going to go through the derivation. The derivation looks absolutely terrifying because it's all notation, it's not specific functions. Heck, something as simple as the quadratic formula, when you see it as a formula, looks kind of intimidating, all the letters, but then when you put the numbers in, oh, yeah, that's all it is, piece of cake. So this will look scary because nothing's going to be able to combine or cancel right away because they're all symbols. But then when we actually do the problems, you'll realize the algebra is not intense at all. So the form I want to start with, okay? Starting with things of the following form. So y, and very specifically 0. This particular technique, we will only work on homogeneous. But do you notice the coefficients? They don't look like numbers anymore, do they? They look like functions. Now, they can be anything, but it will be unusual if there's something other than just simple polynomials, because the algebra starts getting a little too nasty. So the problems that we're going to do today, these will be polynomials. They don't have to be. They could be e to the x's. They could be logs. They could be square roots. But they're basically functions of x in front. So this is second order linear, non-constant coefficients, homogeneous, all of these things. So what we're going to do, first of all, I can't prove this yet. We're actually going to prove this next day. There is a formal proof in the textbook, and it's a good proof, but it's a little too mathy. When I do the stuff next day, it'll be a little more obvious. But the proof showing you how many solutions you absolutely have to have. You have to have two linearly independent solutions here, period. It's not possible to have more, it's not possible to have less. So let's assume that y1 of x and y2 of x are linearly independent solutions. Just so we make sure we understand. If I said to you that, okay, y1 was, e to the 3x and y2 was x cubed. Okay, just what about the coefficients? What about the constants? Well, then we would say the general solution is c1 e to the 3x plus c2x cubed. Understand? When I say these are the solutions, we always say the solutions without the coefficients. Then we say the general solution is a linear combination of those, and the only way I could find the c's is to have initial conditions. And the c's are probably not each one or either, zeros. Okay? So, but we always state the linearly independent solutions in this form without coefficients. So we're going to make one simple assumption, that we actually have two answers. That's it. Then the next thing we're going to do is say, let's let u equal y1 over y2. I can always do that. I have two linearly independent solutions. So I'm going to define a new function. Now, here's the problem. I don't know y1 and y2. But I do know y1. It's given to me. Now, this one seems kind of odd. How could you know one solution? It's actually not that uncommon. We can be working a problem and we've actually discovered a solution. Or somebody else was working the problem and they've discovered a solution and they've given it to us. There are certain situations where we were able to figure out one of the solutions, but not the other one. This only works if I know one of the solutions. Zero. No, zero is not a solution. y1 and y2 are the solutions. So I know y1, meaning it's been given to me somehow. Maybe I figured it out on my own, but I know y1's a solution. So then y1 is equal to u times y2. I know y1. I don't know y2, but I'm going to figure it out. Now this statement here, this is going to come up in a little while, and it always... Where's my eraser?
Right over here.
Who does that? Did you do that? I'm not picking up the nasty rag. That ain't happening. If y1 is a solution, then the following has to be true. I'm going to erase this in a moment, but Does everyone understand? I just replaced the y in that generic statement with the specific y1. That has to be 0 because we just said y1 is a solution. And when I'm all done, I'm going to figure out what y2 is. And it would also satisfy that. This statement is going to come up somewhere in the analysis of the problem. And when this statement comes up, we know, oh, that's equal to 0. And that will greatly reduce all the writing I have. Now, as much as I point that out, it always feels like magic when it happens. I go, well, we can ignore this. Why? Well, because it was that. So what we're going to do is take two derivatives of this, substitute them in here, and then see what falls into our lap. That's how the problem works.
We're only doing this because it's second order, therefore we take two derivatives? Or?
Yes,
Okay.
because I got to have something to put into that guy. Yeah, okay, let me... it's going to be a little bit tight. I'll do them on the left side. I keep having my black pens die on me. One of them's got to work. Okay. No. Oh, that one works. Okay. So, let's go really slow. dy2, I'm sorry, not dy2 dx, sorry. We're saying y1 is equal to this. Or I'm sorry, I'm sorry, I'm going to write this the other way around. I'm sorry. I said we know
y1.
I'm going to do it the other way around. The one that we know, I want to be the one that we're differentiating. I'm sorry. So I want to do y2 equals y1 because I said we know y1. So that means I'm going to write it in this order. It doesn't matter in the long run, but if I have y2 on the other side, it's not going to show up in the equation. I need the y1 to show up. Sorry. I'm looking at that going, something's not going to work there. Okay. So I'm going to take two derivatives of this. So when I do that, so dy2 dx is, and normally when you do a product rule, you always go first times derivative of second and plus second times derivative of first. But I'm going to slightly change that so that I always have them in the same order. So rather do u times the derivative of y and then y times the derivative of u, I'm going to keep it u times y. It's just easier to gather terms. Doesn't change anything. So the first derivative will be first times derivative of second plus the second times the derivative of the first. See what I mean? If I keep the u's first, it's a little bit easier to keep track of in the long run.
These become y2, right? Because that's what we're going to plug into.
No. This statement right here, I said we know y1.
Right.
So this is 0.
Oh, okay.
Yeah, there's not going to be any y2s in our answer right yet. What we're actually going to do is we're not going to find y2. We're going to find u. I mean, not you individually. I meant more like you as a group. No, the other u. You got it? If I find u, and I already know y1, that's how I get y2. We don't find y2 directly, we find u directly. Is everybody cool with that?
Yeah.
But I'm using the fact that I already know y1 is a solution, which means that absolutely this is guaranteed. That's why I needed to do it in this order. I started kind of backwards. Now, the second derivative. So first times derivative of second plus second times derivative of first. And then here, first times derivative of second, you notice something, I have the same thing twice. And then second times derivative of first. Everybody see that those combine? So I'm going to have two of those. So if you'd like, I'll restate that as that equals what we got, u times the second derivative of the y's plus 2 first derivatives of each plus the second derivative of u times the y. So now what I want to do is take that and that, substitute, and that also, and substitute them into there, and combine like a crazy person. Okay? I'm going to erase this. We know it's coming soon. And I do not intend to make any errors, but if you see something, please just point it out, because after a while, it starts looking like the Matrix movie, right? Just symbols everywhere. So I have this times a2 of x, by the way. So a2 of x, u, second derivative, plus 2a2 of x plus a2 of x, and the last one will be second derivative. Now, we're going to take this and put it in right there. And where is that one? U dy dx. And then finally, a0 of x times simply u y1.
We need
Did I
parentheses.
lose anything?
Just parentheses, maybe.
And the A non of X?
Thank you. Yeah, that's hard to read if I don't have.
Also for the whole substitution that we did, right? Does all of that multiply? Oh, I see.
I already put the a2s, the a1,
Oh.
and the a0, so I think we're good.
Yeah.
Is that okay, everybody? It's a lot of stuff, like I said, it's the Matrix movie. Okay. Now, let's see. Let's gather terms now let's get all of the u terms together first. So it might be easier if I identify them. The purely u terms. There we go.
For the y's right next to the du dx's are y1s, yeah?
That's y, yeah, all the y's are y1. Okay, thank you. I think I just left one out there. Yes, it does matter. We want to get that. So let's gather everything that has a u in it. So then I'd have u times a2 of x d squared y1 dx squared plus a1 of x dy1 dx plus a0 of x y, and then plus everything else that's left. Boom. A lot of writing, I know. Not as much as you'd think. Is that right? 1, 2, 3, 1. Yeah. I'm kind of liking where we are right now. Why?
Because of that.
That's my 0. And that's the one I promised you was coming up. It's right there. I just took the y1 and I put it into the original differential equation. So I just lost half of all those terms. So now I'm down to just this. Huh. Now, let's rewrite this one in the order of, how about, let's see, where should we? Hold on a second, what order do I want to do it in? I want to do it in the y's. Where's I have a second derivative somewhere. Hold on, I'm trying to read my own writing here. I have a second derivative.
U with respect to X, right? X squared.
Okay, so that's 0.
Yeah.
Oh, here we go. Yeah, okay, I'm looking at the wrong place. I want this to be first, this to be second, I think, and yes. So let's rewrite it with that one first. We're going to get rid of the a's in a moment, but not yet. So we've got this a2 of x. We have two different du dx terms, right? So how about, let's see, how How can I write that cleanly? I'm not sure I can. A2 of x, 2a2 of x, dy1 dx, plus a1 of x, y1, all times du dx. I think that's about the only way I'm going to do that one. Okay, does that look right to you guys? Okay, I think we did that right. Now, this is still kind of hideous looking until I do what? First of all, let's divide through by the A2. And I'm going to rewrite it like this. In fact, let's divide pretty much by everything. Let's see, which final form do I want this to look like? So I have where's the one?
If we know why.
I lost my U2. Where is it? I can't find it. Oh, there it is. Okay. I've got this. We're going to divide through by the A2 of x. Those are going to be gone. So in fact, we can just call it this. You know. That's just another function. Everybody agree? That's not a big deal. But what that brings us to is the final form of this. It's going to be a y1 times this. That's what we have. Sorry, I keep losing my. There we go. A y1 times this plus a 2 times dy1 dx plus, for lack of a better name, we could call this A3 if you want, or we could call it, how about just another thing, P of x times y1. There we go. And then du dx. Now, what do we usually do at this time?
Divide everything by y1.
But the problem is it's still second order. But you notice that it's got a second order in u and a first order in u, but no u. There's no third term. You see, this is a second derivative, first derivative, and original function. We always usually have that. We have a second derivative, a first derivative, and no original function. So here's where the cleverness comes in. What if I said, let's let w equal du dx? Then what's dw dx? Huh. Why would we do such an outrageous act?
It makes it first order.
Because now what did this just become?
The first order differential equation.
It's first order in w. As ugly as everything is, when we're actually doing the problem, this simplifies so nicely. This is now first order linear in w. So we're going to solve that problem, the first order linear in w. Get an answer for w, and then what? Integrate to find the u. Is it? You like this problem, you don't like getting to this problem. You like this problem better than the first one because it's first order linear and you already know how to solve that. Now, the stuff I did looks outrageous and horrible, but when we actually use specific functions, things start combining and canceling from the first moment on every time. You're not carrying this many terms with you all the way through, okay? So it just doesn't look this bad along the way. The key was, and by the way, I just did the derivation. When I'm assuming I have two linearly independent solutions, I define some random function u as being the quotient, and now I'm finding u, and in the process of finding u, it'll now allow me to find u2. Okay, it'll just fall out into my lap, and I'll find the second solution. But the key was I had to know the first one. Okay, I'm going to erase this in a moment. Question?
How can you get from that to px?
Oh, I said let's just call this one thing. So let's just call that two.
Okay, so just,
You could call it A3 of x if you want.
but still a1x over a2.
Right, but remember, during the course of things, don't we often get rid of coefficients, even if they're functions, divide everything by that, and now it gives you a new look to the problem? That really doesn't present a problem, because ultimately, when all's said and done, I probably don't want something here, right? I probably want this by itself kind of thing. Okay, so I don't worry about things as I go. So let's go ahead and let's do a specific problem. Let's do a couple of specific problems. Again, you're gonna like this. I'm gonna start with a very simple one to begin with. What one? I wrote one down for myself. What did I write down?
This isn't on the test though, right?
No, I think it's the first of the next stuff. So let's do. I am telling you this is one of the solutions, and this is really, really easy to verify. And next day's class, you'll actually be able to solve this one on your own. You're going to learn enough techniques that. So I want to start with one. This is actually kind of low level. Why is this low level? Well, look at my coefficients. They're numbers. That automatically makes it a little easier than if they were variables. But we got to start somewhere. So baby steps, right? Baby steps. Okay. So let's do our thing. So we'll say, let y2 equal u e to the 6x. That's how it starts. That's how we started the last one. So let's do our derivatives now. So dy2 dx is first times derivative of second, which would be 6u e to the 6x, plus the second times the derivative of the first, which would be this.
Is y1, you said y1's gonna be given us always?
One of them has to be given you. Well, I just said, let's just call that y1, because that was kind of the way I set up the derivation. Does it really matter what you call it? No. But remember, you have to have two solutions in the end. And in the end, my y2 has to be a different solution. If somehow or another I come up with the same thing, which I can't, but if I did, then something went wonky along the way. I should come up with something different, and it's probably going to be an exponential function. Just saying, you know.
It can't be like a number like 0.
Well, 0 wouldn't be a linearly independent solution, first of all. Yeah. Think about the Wronskian. The derivative of 0 would be 0. Now you have a column of zeros. Yeah. It kind of violates the rules. Now, go backwards now. C1y1 plus C2y2 is the general solution. Could my C's technically be 0? Yes. That's not the issue. The coefficients could be 0. It's the function that can't be 0. And that's where there's a little confusion there. The functions will never be 0. The coefficients can be. And that does not create a problem, because if I said, all right, let's use 0 as our coefficient, well, that'll work. Kind of boring, but it'll work. All right, so first times derivative of the second, so that'll be 36u e to the 6x. See, I don't see a d squared y dx squared there. Plus the second times the derivative of the first, so that would be 6 du dx e to the 6x. And then I do the same thing here, and I also get 6 du dx e to the 6x, and then finally d squared u dx squared e to the 6x. So I am done literally with all the calculus for a while. So when I put these, and by the way, there's 12. All right. So I'm going to put these guys into the original equation. So I have 36u e to the 6x plus 12 du dx e to the 6x plus d squared u dx squared e to the 6x. And then I have minus 4 of that, so minus 24u e to the 6x minus 4 du dx e to the 6x. And now minus 12 of the original thing, so minus 12u e to the 6x, and this whole thing is still supposed to be 0. Now, does anything combine or cancel?
Yes.
Well, let's see. That, and that do. Does anything else?
We can lose 4 of the 12.
I can combine. Does anything else cancel?
Oh.
No. So what do we got? We got this and then the sum of those two. So d squared u dx squared e to the 6x plus 8 du dx e to the 6x equals 0. This doesn't look anything like the derivation, does it? This looks small and harmless. Well, I just said everything's going to combine and cancel once we actually have specific functions in there. It won't look this ugly. I don't like those e to the 6x's. Can e to the 6x ever equal 0? No. So the 0 isn't coming from the e to the 6x, is it? So can I get rid of the e to the 6x?
Yes.
Yes. So now I'm down to what? Not e, sorry. Du dx. Think of it this way. You factored out the e to the 6x. You factored out e to the 6x. So e to the 6x times something equals 0. Well, it's the something that has to equal 0 because e to the 6x can't equal 0. So after all that, you're down to here. This is a second order differential equation, but since I don't have a u term, I can now make this substitution that will reduce it by 1 degree. So we'll say, let w equal du dx, then dw dx equals the second derivative. So that means my new equation is going to be dw dx plus 8w equals 0. It's a first order linear homogeneous. I think that's about the easiest one there is. You like this so far? This one you should. This is pretty easy. All right? Now there's a series of protocols. If we don't do them right, we may end up contradicting ourselves later. So just follow along and just see what rolls into your lap. All right, so my mu is e to the what?
Integral of p of x. So 8 dx.
So what variable should we be using? Well, same variables we have. So this will be e to the 8x. Oops. No plus c on this. Some of you are writing the plus c and then later ignoring it. If you're writing a plus c, you're already saying it can be any real number. No, you're choosing it to be 0. That's why you're not bothering writing it. This and definite integrals in Calc 1 and 2 are when you get to choose the c. And all values of c give you the same answer. And the answer, you're choosing c to be 0. So don't even write the plus c. You're going to have plus c's in this answer, and they will absolutely not be 0. But this one I get to choose. That's important. Because if I put plus c, then it comes out as a new c times the e, and then it's on both sides, and then it cancels. That's why it didn't matter.
You can choose that C because it has no initial condition to it?
No. Why can I, let's call that c1. Because this is now e to the 8x times e to the c1, which is now c2 e to the 8x. And I'm multiplying both sides of the equation by this. So the very next step is I'm going to cancel all the c2s, which would mean no matter what value you chose, it's canceling from the problem in all scenarios. So might as well choose 0. In a definite integral, you're doing something plus c minus something plus the same c, so those c's always cancel in every scenario. That's why choosing c equal to 0 doesn't change your answer, it just makes it less writing. This is one of those rare scenarios where I get to choose the c because all values of c give me the same. So I multiply both sides here, lest we forget. Now, if I did it right, this should be d dx of e to the 8x w. Is it? First times derivative of second. Okay, second times derivative of first. Okay, I always do this. What's that?
But that equals 0.
Yeah. I'm quite happy with it equaling 0. Less likely to make a mistake. Well, maybe not. Therefore, don't write the integral of the derivative integrated with respect to x. That's just bad notation for two reasons. You just wrote an integral with an independent and a dependent variable at the same time, which technically is impossible. You can't actually physically write that as an integral. Even though a lot of you do, you can't. In Calc 1, when you do a u substitution, you can't have the u and the x in the same integral at the same time. It's an impossible situation. You have two variables in the same integral at the same time, then they absolutely have to be independent. That's Calc 3. But they're not. W is a function of x. So when I integrate both sides, it is e to the 5. What's the other side?
0.
And what does that equal?
C.
So E 5 or
What did I write? Oh my God, those 8s are terrible, aren't they? Sorry about that. Yeah, somebody should make some noise, jump up, down, stomp your feet. Wow. Those could arguably be the worst 8s ever. Okay. The antiderivative of 0 is not 0, ever. There's no conceivable scenario where that's going to be 0. Because then you're saying only the derivative of 0 produces 0. No, the derivative of any constant is 0. No, that's absolutely not 0. If that's 0, we're done. If that's 0, then the answer to my question is 0. No. So therefore, what is W?
E to the negative 8x.
Yeah, so C1 e to the negative 8x. Okay? But wait a minute, I still need to integrate again. So what is U? Well, wouldn't that be then C1 e to the negative 8x? And what is that?
Oh, negative 8c from E.
So negative, how about C1 over 8? E to the negative 8x plus C2. I'm going to fast forward to the final answer. Final answer is going to be, remember I said, whatever your two linearly independent solutions are, your final answer is always going to be a linear combination of those two. So rather than state the two linearly independent solutions, you might as well just state the final answer. It's actually going to arrive sooner than later. So I'm supposed to multiply U by what? E to the 6x, aren't I? But because I already put the constants in here, would it be correct to just go ahead and call that, I don't know, C3? If C is any real number, then negative C over 8 is some other real number. It might as well just do that. Okay. So when I take and I say e to the 6x times u, what does that give me?
C3 e to the negative 2x plus C2 e to the 6x.
And that is the answer to the problem. There's your first linearly independent solution, and there was your second.
Oh, we don't have the C's.
And I don't even have to come up, they were part of my answer. Now, what some people do, and this is very, very risky, what some people do is they'll make all the C's be 0, so they can state their linearly independent solutions as a single term, and then go back and do linear combinations. What's the problem if all my C's are 0? You're not answering this question. Because your answer would be 0, because you have nothing to throw onto the other side. I don't like that method. This is way simpler, because my final answer appeared the moment I multiplied through. And if you do a quick check, these will both work. Now, next day, you're going to learn how to find both of these straightforward. It will be a piece of cake. I use this for us to navigate through this problem because this is about the lowest level second order you're ever going to see. Constant coefficients, simple exponentials. We love exponentials. Exponentials are our friend, our favorite. You don't like sines and cosines as much. You might think you do, but you don't. And I'm going to prove to you next day, if the answer's got exponentials, then everything was real and fine and nice. But if it has sines and cosines, you know what that means? It means every aspect of the problem is imaginary. Sines and cosines cannot come up in a real environment. They can only come up when everything's imaginary. And I'm going to prove that. The proof is trivial. But we don't know enough yet, so you love exponentials. You can live with sines and cosines, but you really love this one.
So do the initial conditions provided satisfy both y1 and y2?
Well, I didn't give you initial conditions. I just gave you one of the functions.
Right.
An initial condition would be something like y of, I would actually, for initial conditions, it would be to solve for the c's.
Right.
And this goes back to Calc 1. I'd have to say something like this. Y of 0 is 3 and y prime of 0 is, negative 5. Oh, now I can go back and now I can figure out the c's.
So would they satisfy both y1 and y2 if
Yes.
we're given initial? Okay.
Yes. And when you're checking a linear combination, you can check it all, or you can check one at a time because it won't make any difference. Either they're all works, or if they both work individually, then their linear combination always works. So at the beginning of the problem, I would hope you check the e to the 6x out. Okay, it worked. Now at the end of the problem, check out the e to the negative 2x. It works. Okay, I'm good. So if one solution works and a second solution works, then we know that every linear combination works because it's equal to 0. Oh, but if it was not equal to 0, now there's other stuff going on. So this is also referred to as the homogeneous solution. Later on, we're gonna do this problem without a zero here. Now, in linear algebra, you guys remember solving systems of equations, there was zero. Then you did one where it was not zero. Oh, so then you have the homogeneous and you have the what's called the particular. The homogeneous was by far the more important. But you had like a secondary solution that you threw on there. The homogeneous, you had the parameter because there was infinitely many. The particular, you had one. When we do stuff, it's going to have a similar feel. It's not exactly the same thing, but it will feel a lot like that. And so we use the same language, homogeneous. So later, right now, this is our answer. Guess what we're going to call this later? We're going to call it YH because it's the solution to the homogeneous equation. But the moment I throw a function on the other side, this is not the solution to that problem. It's only a solution to the homogeneous. So my final answer will be YH plus YP. You with me on that? So the YH only solves the homogeneous, which is by far the more important of the two. And again, this is one of those crossovers from linear, not in how we solve the problem, but in the language we use and what it actually does mean. All right, let's do another one that's a slightly higher version. So what is the point of reduction of order? It is a way of taking a second order problem and making it a first order linear, which automatically makes it easier, but it only works if I know one of the solutions. You would not use this if you didn't know either solution, because the methods you're going to learn, if you can find one solution, you're actually finding both of them simultaneously. Imagine solving a quadratic equation. There's two solutions. Is there a scenario where you could only find one of them, or do they come as a package deal? Right? I found a complex solution, but I can't find the other one, which was the conjugate. No, they generally come as a package deal. So when you're solving these second orders, you're always going to find both solutions. This is the exception that I'm saying, I'm going to give you one, and rather than solve this big old second order problem, which may actually be very difficult, it's really easy for me to find a problem that we won't even find a technique to solve. But if I have one solution, I can use this to find the other one. So let me grab another one. This one's a little ickier. X squared d squared y dx squared plus 2x dy dx minus 6y equals 0. And I'm going to tell you that y1 is x to the fourth. Now, just to make sure, especially because I might have written it down incorrectly, let's check this one, because we did it before. Okay, I need you to actually believe this, not because I just said which one solution. You have the ability to know. So if I put those in there, I'm going to have x squared times 12x squared plus 2x times 4x cubed minus 6 times x to the fourth. Well, that's 12 of them. Did I mess this up? I think I may have. Hold on. Oh, I think I got a boo-boo already. Hold on, minus. Hold on, I copied this directly out of the book. Let me make sure I copied it correctly. Plus 2x minus 6y. Oh, fine. That's what, sorry. You know what I did? That was the adjacent problem. This is problem 10 of the book, but that was the solution from problem 9. By the way, is it a good idea to always check your answers? Yeah, that one wasn't going to work. Woo! I'm glad I checked. Okay. Now let's do a quick double check here. All right, so I don't know why I even thought to check the answer. Okay, 2 plus 2x times 2x minus 6 times x squared. 2x squared plus 4x squared minus 6x squared, does that equal 0? Yeah, okay. I just automatically check, because why? Well, sometimes I write it down wrong. I mean, literally, it can happen. In the previous example, what if it was supposed to be e to the negative 6x? We would have done that whole problem, it would not have worked, and we never would have figured out what went wrong. Well, because that wasn't the solution. X squared is the solution, not x to the fourth. Okay, so now, you never have to show a check. It's kind of implied that when you get to the end of the problem, you check it. I now know that's a solution, so at the end I really would only need to check the other one. So we will let y2 equal ux squared, then dy2 dx is first times derivative of second plus second times derivative of first, and the second derivative, okay, first times the derivative of the second, I'm sorry, derivative of the second, plus the second times, okay, plus the second times the derivative of the first. But aren't I gonna do that one twice? Can we be lazy right here? How about 4 du dx? Because it's gonna show up right here also, isn't it? And then over here, yeah, we went in that order. And then over here, it's gonna be plus d squared u dx squared x squared. Because here, first times derivative of second was also 2 du dxx, which is why that was now 4. I think this is all correct. Again, I need you guys' eyes at all times. It's not an excuse, but I'm the only one that can't see it sometimes. I'm standing too close. So when we put everything into the original equation, just like the previous example, we should expect a tremendous amount of simplification. When I was doing this generically, I was deriving the whole thing, I said, when we regather terms, you're gonna see this large quantity all being 0, and you're going, wow, how will I even know to look for it? You won't. They just cancel. You saw in the last example, they just cancel. I don't have to do anything, I just have to recognize which things cancel. So that large quantity that ended up being 0, those are exactly the terms that are always going to cancel. I'm just guaranteeing you that a portion will always cancel. Can't say what the terms will look like because it depends on the problem. So when I throw that in there, what do we got? We've got 2u plus, sorry, we're gonna put x squared out front, sorry. 2u plus 4 du dx x plus d squared u x squared.
Is there a reason why you're writing it 4 du divided by dx, then dx instead of 4x together?
Oh, well, because when we were doing it, we were keeping the u's followed by the x's all the way through.
Okay.
Well, the difference is the derivative of this guy just was x. But we were keeping u in front of the, no, there's no particular logic other than if we keep them in order, sometimes it's easier. Remedial algebra, you guys remember doing stuff like this. You know, you had 2xy and then you had plus yx, and in baby algebra, people didn't realize they were the same thing. Because they looked different. So there was a reason you wrote things in a consistent order so you could recognize. It makes no difference what order I write them in, but as I go along, it makes it easier to combine like terms. If I put this x in front and then the next one somewhere else, I might not see they're the same term. That's all. That's not a very good reason, but it's good enough. Okay, then 2x times, and this one's kind of a long way, I haven't distributed yet. 2ux plus du dx x squared. And then finally, where is it? Minus 6ux squared. So when I distribute here, 2ux squared plus 4 du dx x cubed plus second derivative x to the 4th plus 4ux squared plus 2 du dx x cubed minus 6ux squared. And that's all 0. Does anything cancel? Do I have any negatives in it?
Yeah, the -6.
Oh, there's a, okay. Starting to feel like I didn't. So 2 of them plus 4 of them minus 6 of them. And that's probably it. Do you see anything else? Not the cancels,
They add,
those combine.
Is it always gonna be the, like, not the first order, but the, like,
The u
yeah,
terms.
U terms always.
When I did it generically, the general form, remember I said let's gather all the terms that have a u, not a du dx, but all the terms that had a u. And then when we pulled the u out, what did we have? We had exactly this with the y1 plugged in. So what did you just find? Only the u terms canceled. And that's exactly my setup. Only the U terms canceled.
So that can kind of be like another check, like where if it all didn't cancel out and something.
Yeah, if I got a U term left over,
We won't be able to do that, right?
well, yeah, I won't be able to do that. If I have a U term left over, there's a problem because now I have too many things. Every term that had a U, not a derivative of U, but had exactly a U, I proved when I factor those terms out, it leaves me a solved differential equation, so it's all zero. But you never have to actually gather the U terms specifically and do the factoring. I just see them all cancel. If I made a bad distributing, that's never going to happen, right? That we distribute badly. I lose a coefficient. Maybe these don't all cancel. Maybe somehow or another I have leftovers and now they combine. Now I go, oh shoot, this is not going to work. But I know they're supposed to cancel. It's an error check that I can go back and see, okay, did I distribute badly? You know, and that's probably the rule. Or it might even go further back. I was supposed to take the derivative of this and get a 2x, but I still have it as an x squared. Or, you know, it could be something like that. But if they don't cancel, you know, red lights should be flashing, you're going to DEFCON 4, all that kind of good stuff. So, when I put together and rearrange it, I'm going to write this guy first. I got 4 of them plus 2 of them, so that's 6 du dx x cubed, and that's all equal to 0. Now, here's an interesting thing. We don't know this yet, but we will know this soon enough. We know that it is always appropriate to get rid of this lead coefficient. It's always legal to divide through by that thing. So tell me, are there any restrictions then on x?
X can't be 0.
X can't be 0. And by the way, we're going to see this all the way to the end of the course. When we get to power series solutions, that's where you're using series. Same thing. If you have an x in front, that x cannot be 0. Because you're always going to be dividing through at some point in the problem to do stuff. And that changes the domain. So since x can't be 0, is that a good thing?
Mm-hmm.
Yeah. It means,
We can divide it.
let's see. Oh, okay, I'm looking at the higher one. So can I do this? Is that legal?
Yes.
It is because x cannot be 0. In fact, we know we're going to have logarithms somehow in this answer. It definitely cannot be 0.
And that also means we'll take the positive domain.
Good point. That's not set in stone yet. It might be the negative side, or I might end up with an even exponent at the end anyway, so it might not matter. Hold that thought. I want you to ask that question later. Because I did not give you enough information really to do, when we talked about the interval of solution, we just said x cannot be 0. That means my solutions at the end are going to be strictly positive or strictly negative, but they're not the whole number line because we had a break. This is something that we're still learning, we're still experiencing, but it's always the whole number line or it's not. If it's broken up, it's still always one interval. It's never broken up, but it can't be this interval or this interval, or I should say, and this interval. It's always an or, and that would be the initial condition that would tell you. Now, what if in the end of the problem, all my x's have even exponents? Then it's a non-issue. But let's say the other solution is x cubed. Now it does matter, doesn't it, whether x is positive or negative. And now it's only one of them will work, and since I didn't give you an initial condition, you don't labor. But if I did give you an initial condition, then you would absolutely know. And that goes back to last day when we talked about the Wronskian. Same thing. If the Wronskian can equal 0, then we change our answer into which interval is appropriate. And without an initial condition, I really can't tell you. I can just say there's only one interval. Don't know which one it is, so I don't worry about it. I don't sweat it. Because I can't give you a wrong answer if I lack the initial condition. But if I have an initial condition, I can give you the wrong answer because I chose the wrong interval. Because the initial condition would solidify which of the intervals it is. So let's finish this one off. It's kind of friendly, I think. I hope. My mu because that's a 6, I can ignore the absolute value. Because the absolute value of x to the 6 and x to the 6 are the same thing. Which is why in this case I said it may not matter. I didn't know ahead of time, but it's not going to matter. And that's kind of a relief. I can't get it wrong.
Why aren't we subbing in W?
Alright, we're working with the.
Oh, I'm sorry. You're right. Nope, I got ahead of myself. We're subbing in the W, folks. What does this look like?
W because the U over dx.
Okay, thank you, I'd say. That would have been life-changing, earth-shattering. Sorry. My brain was working too far ahead of time. Either that or it's fatigue and, I'm just getting old. That's what we're solving, obviously. So that this is gonna go to here. But yes, good catch, because yeah, I can't solve that one technically. It's sort of a wink, wink. I know that we're gonna replace that with a first order linear and then substitute back. But in theory, I can't use a first order linear technique to solve a second order problem. That's why we changed it, and it's artificial. We changed it to a first order problem temporarily in order to solve it, and then we go back. But isn't every time you ever do a substitution and go back, isn't it temporary? Isn't it artificial? But you did the substitution, I'm talking simple calculus. You do the substitution so that you can go back and do the other thing. You did trig substitutions and then went back. Because I couldn't solve the problem as is, I did this cool trick and then I changed it back. So that's what we're doing. When I multiply both sides by this, I'm going to have x to the 6th dw dx plus 6x to the 5th w equals 0. And if I did it right, this should be the derivative of x to the 6th w, and boom, 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 yes it is. The fact that the right side equals 0, I know some of you, that bothered you in the last problem. Please don't let it bother you, because it's always going to be 0. Why is it always going to be 0? Because the original problem's homogeneous. Yeah, I'm never going to have anything on the right side other than a 0.
You mentioned earlier because that 6, like the absolute value of the log would go away because of the 6. Would it not go away? Like what number would it be for it not to go away?
Well, if it were an odd number, absolute value to an odd number is strictly positive quantity. So could I in theory just drop the absolute value? That's where you got to be a little bit careful. So we're writing the solution as if it's always positive, but what if it was allowed to be negative? Then I would have to say, I might have to tweak that. I might even have to make it the negative of the answer. But without an initial condition, that is not a cause of concern.
Okay. So we can just assume that it's always going to be positive?
For the purposes of writing it and finishing the integrating factor, because that will work every time. It's always going to work in this capacity. But yeah, it should make you feel a little uneasy if you're just ignoring, there's an absolute value here. But our real question is, if x being negative changes the answer, then I have a concern. But if x being negative doesn't make it a different answer, then I don't have a concern. We got lucky. But if that was odd, I have to be mindful of it, that's all.
Then we would just assume that it's on the positive numbers.
For now, yeah. And if it turned out it was the other side, then we'd just use a negative. But again, that's probably not going to come up. That is all correct, but you're diving into a deeper, more complicated problem, but it is still correct to consider these. The problems we're working now, it's probably a non-concern for the most part. Just have it in the back of your mind. You all realize it is kind of sloppy when we're doing these and we drop the absolute values, because we just had a recent quiz where people had absolute values and they're pulling things out of the square roots and just ignoring the absolute value. But wait, we already said it could be negative, and then we pulled it out as a non-absolute value. We just lost half the number line when we did that. There are certain things I don't want to do because I don't want to lose something. When I integrate both sides, and now I have this, I can't have a 0 on the right. Now, interestingly enough, a lot of the textbooks will say, no arbitrary constants, keep everything 0. But the problem is if that's a 0 on the right, that means W is identically 0. Which means I don't have much of a problem here. Because then my antiderivative would still be 0 because we already said we're integrating 0 to get zeros. Bad calculus. Bad calculus. Like bad dog, right? So for now I'm going to write it like this because I got to do some more stuff. So then U, which is the integral of this, now go slow. What's this going to be?
-5.
negative C3.
Oh, yeah.
Well, let's get that part right first, and then I'm going to call that C3. You're going to find the majority of your answers don't have C1 and C2. They're going to have C3 and C2. Now, if you want to be really clever, call them C and C2, and then change it back to C1. The one mistake that I keep seeing over and over and over again is we're using the same C in multiple places when it absolutely can't be. For example, we'll have C equals e to the C, which is kind of impossible. First of all, the line y equal x and y equal e to the x never intersect. So there's no real or even imaginary number where e to the c equals c. So I like this relabeling. Yeah, C3. I'm fine with C3.
Do we not need to be worried about the negative sign attached to this?
Well, if that c can be any real number, when does that matter? Things like that matter, for example, if I have an exponential that can never be negative, and now I'm making an arbitrary constant, it can't be all real numbers, it can only be positives. That, does it happen a lot? It happens enough. You know, that we have the arbitrary constant in the exponent, so now it's strictly a positive constant. But that's, again, it's not going to change what you write. But just be mindful that I can't have now every real number basically as an answer. So I've got this. I have one step left.
Multiply it by x squared.
Multiply it by x squared. I'm running out of room here. So if I take x squared and I multiply it by c3, x to the negative fifth plus c2, I get c3 x to the negative third plus c2 x squared. Now, you already checked x squared. Do you think it would be wise to check x to the negative third? Yeah, strangely enough, there is an error. It's not a common error, but I do teach primarily calc and above, and I've seen this error actually double-digit times this semester. People multiplying x to a power times x to a power and not adding the exponents, but multiplying the exponents. That's happened in this class actually several times. It's carelessness, but that's a killer, wouldn't it? So if I wrote x to the negative 10 here, who in the world would write that? Well, look next to you. They may have. Okay. I didn't say which side to look, by the way. No, you're automatically looking at each other. Okay, it could have been the other side. That's an error. It's a silly error. But that error actually does happen. And in a calculus class, it happens a lot because our minds are already way past that. But we make these silly exponent errors. But is that a killer? Yeah, it's a completely different answer. So I would take the x to the negative 3 and do what we did at the beginning with the x squared just to ensure. Now, yes, you should write it as c3 over x to the third as your final answer. But when you're checking it, you probably want to check it in that form, don't you? Easier to take derivatives of. Should you always reduce things like that? Well, yeah, is it life and death? Is it going to change things if I don't? No. And, you know, to be quite honest, I really don't care if you left it as x to the negative third. There are times when you do need to simplify, but it's probably not that. Things like having fractions in the numerator and or denominator. No, that's one we want to clean up. What about things like roots versus fractional exponents? Do you ever need to worry about that? No. The common one, and some of you guys are guilty of this one, is you'll get something like e to the negative x as an answer, and you say, well, I got to write it like this. And I'll say, why? First of all, I can't integrate that, and I can't differentiate that. In fact, I can't even evaluate that easily on my calculator. So no, leave it like that. Why? Because that is simplified. Why is that simplified? Because that exponent is not negative. The exponent's not even a number, it's a variable. Isn't negative x always negative? How often is negative x negative? Half time, but it's positive the other half. Oh, e to the negative 2 I should write as 1 over e squared. But e to the negative x isn't a negative number. And this is not incorrect. But I see no advantage whatsoever. No, leave it. All the calculus you do that. If you're doing this on Desmos, you do this. If you're evaluating this in your calculator, you do this. There's no advantage. It's not wrong. But I'm going sideways without it improving. So I'm just saying, if you left it as x to the negative 3, I don't have any problem with that. You know.
Because this is kind of what you always talk about, how like you want to leave it in the way that's going to be most used.
Yeah, let's face it, I got to check my answer. I don't want to write it as a quotient. I want to check it like that because it's really quick. There will be times when I do want to rewrite it because maybe I'm going to combine it with something else at some point. Maybe my answer is it's being multiplied by another function, and now writing the thing as a quotient might, I don't know, I can't even say what, all the possibilities, but everything is on the table. Don't worry about the final form too much if your final form is correct. Are there times you can simplify things that makes it easier? Yeah, I mean, an unreduced quotient. Nobody would say, and the answer is 8 over 4. Right? You'd probably simplify that. But there are other times when it just, there's no logic, and we overkill. things like with roots, a lot of times people overkill it and they keep going and they end up going exactly the wrong direction. They actually made it unsimplified because they kept going. If you can simplify it and the simplification is obvious, I say always take it. If it can be simplified but you don't see it, or you look something up and go, wow, that looks really complicated, leave it alone. Leave it alone.
I have a question. I might have missed this when you did the first example, but you said we were gonna shortcut to the answer, combining the Y1 and Y2.
Right, because did we ever actually say in our answer what Y2 is? Did we find specifically Y2 all by itself?
Found you.
No, the method actually gives us the whole answer. Because Y2 is right there, but Y1 is right there.
Oh.
I've never actually said Y2 equals, I gave you the final answer, because the format that we're using to find it, because we're leaving the constants in, it's literally fast forward you. If you found Y2 specifically, the answer to the question is usually give a general solution. That's usually the answer. So we are going to work things next day where you won't have this luxury. So you're going to find Y1 and Y2. Maybe there's a Y3, maybe there's a Y4. And you found each one individually. And now your general solution is going to be C1, Y1 plus C2, Y2. And you're just going to state it. There's nothing wrong with not finishing it, but usually we say, what is the answer? You know, what function solves this? Okay, it's the linear combination of all my linearly independent solutions. This is a linear combination of two linearly independent solutions, but I kind of found them simultaneously.
So we were given that one's Y1, so the other one must be Y2.
That has to be Y2. Yeah.
My only question, my confusion was, we said Y2 is U times X squared, and then we found U.
Right, but because we found U by leaving the plus C's in there. The only way we could have found Y2 separate from there is to make one of my C's 0, but not the other one, which is really tricky. And to me, it's extremely inconsistent. If I made the first C not 0, but I made the second C 0. So how does that work? How do you integrate 0 and get two completely different and contradictory results? I have a problem with that. I'd rather just do it this way. And know that my final answer is always embedded in there. In fact, it's less work in the long run. And then you don't, if you're doing a step where you're saying, it just doesn't feel right, it's just something weird about that. You know, you go, okay, then maybe it's not, but I got the right answer, but wait a minute, I got the right answer because I did the same thing two different ways. That's iffy. You know, this is a special technique. It sits all alone, all by itself. You would not choose to use this as a method of solving unless you already had a solution, and that's going to be rare. It does happen. In fact, I used to go as far as saying, look, it's kind of silly to think that you're going to be able to find one of them and not the other. No, you're always going to find both. But it is actually possible, and I've seen situations where we know this is a solution, maybe by trial and error, maybe because it was a really gnarly problem and somebody figured out one of the solutions through pain and suffering. But there are backdoor ways of finding things that are really complicated integrations, but we do have one solution. And now I can find the other one. I can create a problem that has a solution. I can make it really icky, and now this problem cannot be solved by any method that we're going to learn. It's actually really not that hard. Let's take this problem right here, and I can think of the exact problem. I'll go back to the exact problem. Let me take a really simple potential function. Let me take the partial derivatives to make them m and n, and now let me divide everything by x squared, or multiply everything by x squared. Now it's not exact, and now I have to calculate the integrating factor. Do you remember that? I did a problem like that in class, and now we got the answer. I had to reverse engineer it. I can do that with a differential equation that's solvable. I can reverse engineer it to now make it not solvable, but I know one of the answers. Now I'm giving you something you can't solve using any technique that you now know, but because you have one of the answers, you can use this to find the other. That is not a common problem. It's rarer than the others, but it is a technique, and it's one to have in your back pocket. If given the choice, you don't generally choose this one because it's longer than the other techniques. In some cases, it's a lot longer. We do have one other technique that is a very long technique. It's called variation of parameters that's coming up, but when you use it, it is because nothing else was going to work. And it's a very powerful technique. It's not hard, it's just not short.
Are you gonna put like a question that's like shorter on the exam, like so we don't lose all of our time doing like?
Are you talking about this?
Yeah, for this, like for exam 2.
Well, I mean, this question right here is pretty straightforward. I mean, there's nothing complicated about this, and the derivatives weren't bad. I almost did one, just so you know. I was looking at the textbook and I was looking at problem number 12 and I thought, oh, that's a great one. Y1 was x to the 1/2 times log x. And then when I started doing it by hand, I went, nah, we have to use the product rule multiple times and our second derivative is going to have 8 terms. And I'm like, nah, I think we'll skip that one. That's a great practice one at home. That one is awful. It just, as this, because the algebra in that one is so, it's more than double this one, because it's a product of functions. We're going to learn how to solve that one directly anyway later on. That one has a direct solution. But for this type of problem, I would not give you a complicated one, because I don't want you getting stuck on the algebra part. I want you, but because you don't have to rederive, right? You just did what we did, you plug it in and boom.
For the exam, would we be asked to find the general solution rather than like just the y2 portion?
Oh, most of the time, your general solution, because you're going to find there are problems that are going to be higher than second order. But if they're higher than second order, it means they were easy. The level of difficulty of a second order problem is set. There are problems, and I'll keep it a simple way. Everybody here can solve a quadratic, even if you can't factor it. You can use your quadratic formula. Can you all solve cubics?
Calculator has a cubic formula in it.
Yeah, but can you solve it?
No.
Can you solve 4th degree or 5th degree in general? No. Oh, but what if I said I want you to solve a cubic, but the constant term is 0? Oh, I just factor out an x, and now it's easy. I want you to solve a 4th degree polynomial equation, and the constant and linear terms are both 0. Now it's easy, I can factor out an x squared. Are there higher degrees that are still easy? Yeah, if I eliminate some of the terms. So it's the same thing with the differential equations. There are things that are higher than second order that won't be any harder because, look at that problem for a moment. Can't I kind of treat that? Yeah. So if I gave you a 4th order, but I eliminated everything, past the 3rd, it's kind of the same problem as this, isn't it? So I'm going to show you that some of the higher order problems are actually going to be easy because I'm going to eliminate certain terms, and the algebra you use to solve it will feel exactly the same. I don't want to go into too much because that's the whole next day's lecture. Not complicated at all. Let's go do that.